Welcome to the SCM department. In our department we research molecules, individual molecules, and how they interact with other particles such as atoms, electrons or other molecules. This is very fundamental. We would like to understand how a quantum mechanical object, like a molecule, really behaves in its most fundamental form. And for this we develop and build unique equipment to control molecules in all their degrees of freedom and then let them, for instance, collide with other particles and detect what is happening to these molecules. Our research is very fundamental, but it's also right in between physics and chemistry. We use the methods of the physicists, like particle accelerators, lasers and advanced detection schemes. But our research goals are often also linked to chemistry. For instance, we would like to understand how reactions follow, how molecules collide with each other, or even we can look at molecules in their ultra-fast timescales as they are interacting with each other. So if you'd like to learn more about our research, please come and visit our department. Our department consists of 3 separate research units, and in the following movie you're going to see what each of these 3 research directions can bring for you. I hope you enjoy the movie and I hope I'll see you back in our department in the future. In order to do our experiments, we really need to build our own machines because they are not for sale. And in doing so, we really push the technological limits of what is possible to control our molecules. Please have a look at this video in which we detail what all is needed to make an experiment work. So in my group, we try to understand collisions between individual molecules. But what's very special is about our research is that we try to do this at very low temperatures. Basically, we would like to reach the lowest temperatures that are possible. Basically 0 Kelvin. And so why is this so interesting to go to these very low temperatures? Well, that has everything to do with quantum mechanics. As you know, nature, like atoms and molecules,
start behaving very differently at low temperatures than when they are at high temperatures. They really start behaving like quantum objects or like matter waves. And these matter waves simply collide very differently than as they collide at high temperatures. At high temperatures, a collision between molecules can really be seen as the collision of billiard balls, as you're used to on your billiard table. But at low collision energies, this description completely falls apart, and we have to go to the quantum mechanical nature of the molecules. Basically saying that molecules are now waves. And as waves come together, they can do special things. They can start to interfere and so forth. Well, this of course is well known already from the early days of quantum mechanics, but surprisingly, in these type of molecular collisions, these quantum effects have only barely been seen. They have been predicted decades ago by theoreticians, but experimentally it has proven extremely difficult to reach these very low collision energies and to reach the sufficient levels of control to actually see these quantum phenomena. And in my group, we have developed techniques that allow us to really measure these properties of cold molecules at the most fundamental conditions. We have built so-called Stark decelerators that allow us to achieve full control over molecules. We can really take individual molecules, slow them down or speed them up, and let them collide under extremely controlled conditions with each other. And if you do this at these very low temperatures that we can achieve, you can really start seeing this quantum mechanical matter wave effect. And this leads to mechanisms in collisions like scattering resonances and diffraction, all kind of things that we really would like to probe in order to really learn about the fundamental nature of molecules and the world around us. So if you are triggered by this, please have a look at our laboratory and come and speak to us.
Hi everyone, welcome to this online lab tour. We are the PhD students working for the Spectroscopy of Cold Molecules department on two quite similar experimental setups with a Stark decelerator. And we would like to show you all the components of these setups and how they merge together in an experiment in order to get an idea of the research we're doing. So the first component are the gases, which we use to perform our collisions, of course. In this left image you can see the different gas tanks in which they are stored. And the gases are often mixed in with a so-called seeding gas, which is a noble gas such as xenon, which we see in the right picture. So let's see a video in real life of how these gases are introduced to our setup. So first I will walk to the part of the setup where our mixed gas bottles are located. And from one of these gas bottles I will introduce a little bit of new gas into the gas line. And then we can also see a pressure increase because of this. And it follows this gas line and then enters our system. So it enters a valve, which is seen on the top right, this orange thing, which produces a molecular beam for us, which is then passed on to a skimmer, which selects only a central part of our molecular beam. And then it enters our Stark decelerator, of which a real life picture is shown on the bottom right. So this was a short video of our almost 3 meter long Stark decelerator, which is shielded from the outside world because we also of course need high vacuum for our experiments. So what does this Stark decelerator do for us? Yeah, we apply high voltages, as you can see in the bottom right for instance, to alternating horizontal and vertical rods to create electric fields, which we then use to manipulate our molecular packets. So these fields must be turned on and off at specific times, which we can see in the top right, to tune this molecular packet to a desired velocity and with the small velocity and spatial spreads, which we need for our collisions. So now Stach will elaborate a little bit more on some of the other components of our setups.
To see our molecules and measure the effect of the collisions, we use lasers. The ones you see here are called dye lasers because they pump an organic dye through these tubes to generate light. When we turn on the light, you can see that each dye generates a different color range. With the right wavelength, we can ionize our molecules and turn them into ions with a positive charge. This makes them susceptible to electric fields. So after having flown all the way through our decelerator, the molecules collide with a second cloud of gas. At the same time, the laser enters through this window, ionizing the particles. We use electric fields to shoot them upwards until they hit a phosphor screen and generate a flash of light that is picked up by the camera on the top. Unlike normal optical lenses, which image position, we use electrostatic lenses that can image the velocity of our particles. This technique is called velocity map imaging. This means that the position at which our molecules eventually hit the detector tells us something about their velocity. By accumulating many events, which can take several days, a pattern starts to appear. We can see the quantum waves. Our images have superior resolution because we use a Stark decelerator to prepare our molecules before the collision and a VMI detector to interrogate the molecules after the collision. As you can already tell, we generate a lot of raw data, so part of our time is spent on data analysis. At the same time, we perform detailed simulations of our experiment, based on the latest predictions of theoretical chemists. We make use of several programming languages and applications to help us do that. So, we combine all these components to create an experiment that probes cool, fundamental physics. Hopefully this has given you an impression of the work we are doing. Thanks a lot for your attention.
So our aim is to investigate and control chemical reactions, or as we call them, reactive collisions. And if you compare them to the collisions you saw previously, then what makes these reactions is that chemical bonds are broken and new ones are formed. So in the previous reactions, molecules and atoms stayed intact, but we investigate systems where they react and really form and break chemical bonds. And these are, for instance, very important when we want to make new materials or molecules, but also in your body, atmosphere, interstellar media, and combustion processes. And if we want to understand these environments or processes, we need to understand what happens during a chemical reaction. So how are these bonds actually broken and formed? And that is something that on a molecular level is not so well known. And so that is what we want to investigate. So we fundamentally want to study what happens during these reactions. And we do that in very high detail. And when we have a very good understanding of these reactions, eventually we could even try to control them and make sure that certain reaction pathways are not possible, to, for instance, prevent byproducts that you don't want to have. And so how we do that in our bottom-up approach in the lab is something that we would like to show you in the lab. So I would like to invite you to join our virtual lab tour, where Vikram will show you around in the lab. And actually this lab you can easily see from outside when you're waiting for the traffic light or so.
Hi, I'm Vikram and I work at the Spectroscopy of Cold Molecules department on our Zeeman decelerator project. And what we do in this project, we study collisions between magnetic particles and the secondary species. And to learn about these collisions in great detail, we need two things. We need to know before the collision exactly what we send in, which means to have great control over the particles. And after the collision, we need to measure the particle details, so their exact properties. And to do this, we use a few experimental tricks. So we start by expanding gas into high vacuum, which is typically 10 orders of magnitude lower pressure than atmosphere. This generates a beam of molecules that passes through our setup. To control the magnetic particles that are in this beam, we use our Zeeman decelerator that consists of an array of solenoids and hexagons. So the solenoids, they consist of a copper capillary through which we pass high currents. This generates a magnetic field gradient along the axis of the coil or along the axis of the molecular beam. And this can be used to manipulate the velocities of the particles in our beam. The hexapoles, on the other hand, they consist of permanent magnets and make on the axis perpendicular to the axis of our molecular beam, they generate a field gradient to keep the particles together throughout the deceleration process. So our Zeeman decelerator consists of a total of 100 coils and hexapoles, which you can see in a clear aligned array in our machine. So we pulse very high currents through these solenoids of about 5 kiloampere, and to do this we have custom built switching electronics. Also, because we pulse these high currents, the coils get very hot, and to prevent them from breaking down, we use a direct cooling approach to prevent them from overheating. So the molecules travel through our decelerator and then enter our detection region. However, one beam of molecules does not make a collision, so we need a second beam of molecules that we generate here. We again expand gas into high vacuum, but this time we use a simpler method to control the particles in this beam, which is to cool down this valve with cryogenic technique to around 30 Kelvin. So this beam also enters our detection region where they cross and collide. After the collision, we need to detect our particles. And for this we use high power UV laser systems. And this state selectively ionizes the particles after the collision in our detection region. Then, using electric fields, the ions are accelerated up through this flight tube and hit the detector. And if we do this in a special way, we can also learn about the velocities of the particles after the collision. So this means that we know the two things, the quantum state of the particles after the collision and their velocity. And this gives us full information of the products that are formed in our collisions. And this is, in a nutshell, our Zeeman scattering experiment. So let's take a walk to the other side of the lab. So first of all, we have another more compact machine on which my colleague Shudong is working at the moment. And this setup we use to develop new detection methods and test new species before putting them in the larger and more complicated Zeeman setup. But we of course also have to analyze and acquire our data. For this we can take a walk to our data acquisition computer. So the ions we detect, they appear as bright flashes of light. And if we acquire these for a long enough time, we will typically obtain an image that looks something like this. So what you can see here is there is a ring that appears, and this is because the molecules can fly off in different directions after the collision process. And what is now very interesting is to look at the fine details of this distribution of intensity that we can resolve with our high resolution experiment. And you can clearly see there is some oscillatory structure along this ring. And this is due to the wave-like nature of the particles during the collision. It is an interference effect that is dictated by quantum mechanics.
So this is how we are studying reactions, and in case you're interested, feel free to contact me and we can show you around more in the lab.
Hi, I'm Daniel and welcome to the Ultrafast Chemical Dynamics. Now in my group we study molecules, their properties and interactions at ultra-fast timescales of femtoseconds. Now a femtosecond is 10 to the minus 15th of a second, an unimaginably short period of time. But this is also the natural timescale at which atoms move and energy is redistributed within molecules. What we are interested in particular is the question of how do molecules deal with excess energy. And while this might sound like a very academic question, it's actually highly relevant all around us. Think, for example, about the sun hitting your skin. Will it heat your skin up or will it give you a sunburn? It's all a question of how the molecules in your skin deal with the excess energy from the sun's UV rays. Now we study these processes in the lab, making use of state-of-the-art ultra-fast laser systems and highly controlled molecular beams. We then put a certain amount of excess energy into a molecule, for example using a UV photon or by bombarding it with an electron. And we then watch what happens. And we do that using spectroscopic techniques, and in particular we use photoelectron spectroscopy. This allows us to directly monitor the electronic states of molecules. And we do this, of course, with femtosecond time resolution, so we can directly track or watch the flow of electronic energy through molecular systems in real time. And to see how this is actually done, I will now hand you over to some of my students that will show you the lab.
Hi, I'm Anna and I will explain you the basics of the femtosecond laser. This is the first step for all of our ultra-fast spectroscopy experiments. It begins with the generation of an 800 nanometer pulse, as you can see here, by a titanium sapphire laser. And then these ultra-short pulses, which are about 100 femtoseconds, they can travel through the laser table and we direct them to any of the experiments where we need to use them. The fundamental wavelength of our beam is 800 nanometers, but we are usually interested in shorter wavelengths because we need to excite the molecules to an electronic excited state. And to achieve these shorter wavelengths, we can use harmonic generation in a nonlinear crystal. So, for example, with second harmonic generation, we can go from the 800 nanometer photons to 400 nanometers. We can also use third harmonic generation, in which we combine the 800 plus the 400 we just obtained, and that gives us a wavelength of 266 nanometers, which is in the range where many of the organic molecules we are interested in can absorb well. So there is another device that allows us to tune the wavelength of our beam, and this is the non-collinear optical parametric amplifier that allows us to choose the wavelength we need to probe our to study our molecules. As you can see here, for example, now it's tuned to a yellow wavelength. And in addition to this tunability of wavelength, we also have another advantage, which is with this prism compressor, we can obtain even shorter pulses than we did in the beginning. So we can go to shorter than 127 pulses. So in some cases, we want to study the dynamics of our molecules, and then we need not only one pulse, but two. The first one will excite the molecules and start the dynamics, and the second one will allow us to take a snapshot of the molecule, and then by taking snapshots at different time delays, we can reconstruct the dynamics. To modify this time delay, we use a translation stage. So when we move it, we change the time delay between the two pulses, and then we can, it means that if we use, for example, a translation of 15 centimeters, that will introduce a 1 nanosecond delay. After, we can recombine the first pulse with the second one and focus them into the chamber where we can perform our experiments.
Hi, I am Greta and I will show you my machine where I study light-induced dynamics of biomolecules. Biomolecules are a bit difficult to do this light-induced dynamic studies on, since biomolecules have isomers. Isomers are different structures of otherwise the same molecule. These have very different properties also in biology. We do our experiments in gas phase, and in gas phase different isomers of the same molecule are present at the same time. But luckily these different isomers have different dipole moments, which makes it able to separate them using a strong electric field. We do the separation with a device called an electrostatic deflector. This device consists of two electrodes with a very strong electric field in between them in the order of 100 kilovolts per centimeter. This field exerts a force on our molecules, essentially giving them a kick, and this separates the molecules in space in our machine. So now I'll show you how we do this in the experiment. Our experiment consists of big vacuum chambers, since we want to look at individual molecules, and if we would do this in atmospheric pressure, we would only be probing the air around us instead of the molecules of interest. So our experiments start with in the source chamber. In this chamber we have a valve. In this valve we then put our sample molecule. Then we heat up the whole valve, including the sample molecule, to bring it into the gas phase. We then put noble gas through this valve to expand our molecule along with the noble gas into the vacuum. After the source chamber, we go through a skimmer to select out the center and best part of our beam, and we go into the deflector chamber. Inside this deflector chamber, there's our 30 centimeter long deflector. In this deflector, we deflect the molecules upwards based on their dipole moment. The highest dipole moment will be most deflected upwards. Then after this deflection chamber, the molecules enter the deflection chamber. In the interaction chamber of our machine, our isomer-selected beam is intersected by a bump and a probe pulse. This first pulse, the bump pulse, excites our molecule to an excited state, and the second pulse, the probe pulse, ionizes the molecule, and we detect it using post-electron spectroscopy. This means we ionize our molecule, we create an ion and an electron, and we detect the electron we create using velocity map imaging. By measuring the kinetic energy of this electron and knowing our laser energy, we can determine the energy levels of our molecule. And by changing the time delay between our pump and our probe pulse, as Anna has shown you earlier, we can map out the electronic state and the population of our molecule in real time. This will really tell us what's going on in our molecule, if it heats up, for example, or if it dissociates, and tells us why.
So we hope you enjoyed watching the video of the research we do in our department. We hope we have triggered you for interest in molecular physics, and if you want to know more, please come and talk to me, Jolijn or Daniel, and we make an appointment and show you even more.